Greetings, geomorphology class. Today we're going to be talking about geomorphologists and the tools they use to start to quantify the topography of the surface of the Earth. So today we're going to be talking a lot about what geologists use to actually measure changes in the Earth's surface. We'll be talking about what that means in terms of relative elevation changes, like trying to characterize how steep a hill is and how much change in elevation there is along a hill, but also like quantifying elevation too in general, like saying that that hill is at 3,000 meters in elevation relative to sea level. So that's our goal today, to talk about the different ways that in the field geomorphologists are able to do this. So the picture here to get us started, actually I should jump to this side out of the way. These are a couple of field assistants of mine in Yellowstone a couple of years back. And the great thing about being a field geologist like this is you get to schlep your gear out into the backcountry where you can do this type of work. Okay, get my pointer working here. There we go. So there's lots of different types of topographic environments at the Earth's surface. And so the tools you use are going to change based on what you're trying to measure and how accurately you're trying to measure that. So here we've got some examples of different types of topographies and landscapes. We've got beaches here, so where you have relatively little elevation change, but you might need a high degree of accuracy. Or we've got some waterfalls up here, and in waterfalls you might have a significant change in elevation you need to quantify, but you also might have some trees that are in the way as well, and that can be an issue depending on your method. So we'll talk about these different methods we use to characterize topography at the surface of the Earth. Okay, so this is the picture from your textbook of from Bierman and Montgomery, and what I wanted to do, let's see if I can get this highlighter working here, is kind of point out that when we're talking about characterizing elevation, we can do it from a ground-based system, which is kind of optical surveys that is shown in one here. All right, we can move from that to kind of a handheld GPS survey. We'll be talking about these, or we can look at recording with great degree of detail repeat measurements of an installed base station, or we'll actually talk about airborne acquisition of survey data, and then space-based acquisition of survey data as well. So that's what we're going to cover here in the next couple of minutes. So if we think back, probably the easiest way to measure topography is using a plane table. And plane tables were how we used to do geographic surveys over 100 years ago, before the inventions of auto levels or lasers. But I bring it out and mention it because this is kind of the foundation of our field. And so how one of these surveys would work is you would essentially have a horizontal table. So here's our horizontal table right here. And you have that perfectly horizontal, okay? And then on that, you set an Adelaide. And once you have that set, you can sight to different positions in the landscape. So here you're using the Adelaide to sight out to the position. And based on the angle and the distance to that position, you can have a piece of paper right on your plane table that you actually record the elevation positions. That's about all I really want to say about plane tables right now. We don't really use them anymore in the field, but it's worth noting kind of the background. And it really wasn't that long ago, maybe 40 or 50 years ago, that when you would take geology field camp, part of your field camp training would be using a plane table. So these are still in a relatively recent memory, but not so much anymore. Okay, the next step up, and something that we use all the time in geology, is an auto level. And all an auto level is it's basically an optical instrument that allows you to get a perfectly level line. And so you set the auto level up on your tripod here, and then the auto level itself, you'll set it so it's level, and then when you sight through it, you can sight and have a perfectly horizontal line that you're sighting through. And so all it does is allow you to see directly across. So this is kind of similar to our hand level, right? Remember oh wait, this is going to be before the hand level video from our lab this afternoon, but you'll learn that you can also do this just with a level bubble in a hand level as well. And actually, I might have one of those right here. Yes, look at that, I do. So here's our example of a hand level that we used on the big sink that you'll be seeing this afternoon. And so an auto level and hand level work in exactly the same way, where you basically can cite a horizontal line, and then from that you're allowed to, you can go and set up a rod. So here's Dylan with a rod here, and these have numbers on them that give you the elevation, and so you can determine how high, how much below you the elevation of the ground is based on the numbers on your measuring stick. In our lab next week, we'll talk a little bit more about how auto levels work. Okay, going a step up from auto levels where we can increase our accuracy and precision is going to be an electronic theodolite, or what's known as a total station. And so here's an example of a total station here. A total station essentially sends out a laser pulse that is then reflected off a target and then reflected back to the total station. So it sends out the laser pulse, and then the return back to the total station. The total station is able to very accurately measure the time it takes for that laser pulse to get back, and based on that time, it can determine the distance. The auto level as well has very sophisticated gyroscopes in there, and it can also determine your angle as well. And so this allows you to measure changes in the Earth's surface down to millimeters. And you'll see these used at construction sites and on road building sites all the time. So these are a couple of students using the auto level in Yellowstone National Park last summer. Okay, and here's just another example. I'm going to highlight, put this in your brain, that you can actually pair GPS surveys with total station surveys. So that's kind of, you can use these in conjunction. We'll be talking about GPS right now. Okay, so the next level in terms of doing surveys and measuring topography is using GPS, geographic positioning systems. And so GPS allows us to measure elevations all over the globe to a very, very high degree of accuracy if you have the right system. So we use a lot of GPS in our research. Here's our TopCon receivers here. We often will use them in pairs. So here's a base station, and then here's a rover here. And this allows us to measure elevation changes very, very rapidly once you get the system up. There's a bit of time in getting them up and running, but once they're up and running, you can collect a lot of data relatively quickly. Okay, so when we use a GPS system, really, because these are satellite-based, kind of how you report where you are can be done in different ways. And so you could present your position in what's known as a Cartesian system, where essentially you're you're asking for your elevation based on essentially a known point at the center of the Earth and your position in X, Y, and Z from the center of the Earth. Or we can use what's called a geographic coordinate system, which you are probably most used to. A geographic coordinate system assumes kind of a simplified shape of the Earth, and once you do that, then you can just report your your position as a latitude and a longitude, right? We often do this in lat long in degrees, where 0 degree would be the equator, and latitude you would go up to 90 degrees, which would be the North Pole, or negative 90 degrees, which would be the South Pole, and then your longitude is your distance in degrees from the prime meridian here in England. So you can report those in lat long, and it's a simplified, you don't have to think about where you are relative to the Earth's center. Instead, we often use your elevation relative to sea level. You can also use projected coordinate systems. And in projected coordinate systems, what we're doing is we're taking that three-dimensional sphere that is the Earth and simplifying it and turning it into a flat 2D map. And we can use the UTM system that you've probably heard of, or maybe the state plane system to do that. So generally in surveying in our world, we use either geographic or projected coordinate systems. That's all I want to get into it right now. If you're really jazzed about coordinate systems and map making, please take Nick Bader's GIS class, because you can go into this in a lot more detail. Okay, so here is our GPS system. The U.S. Department of Defense has officially named our GPS system in the United States Navstar. Okay, this system was started in the late 70s, and we had our full constellation by the mid-90s, when really you see the use of GPS explode around the globe. These things don't last forever. They last about 10 years, and we send up new ones constantly. These things are pretty big, and they are powered by solar panels, so you get continuous power to these things. So that's kind of what a GPS satellite looks like. Here's the picture of it right up here. Okay, so how does GPS actually work? What are you actually doing? Well, all we know is the GPS has to be sending down some sort of signal that your GPS receiver receives, right? But what is the GPS actually sending out? It can't be sending out your position. It doesn't know your position. It can't be sending out its position in space. How would that particularly be useful to you? What is it actually sending out? This is kind of interesting. What they're doing is essentially your GPS receiver is picking up what time it is. Pretty cool, huh? So all of the GPS receivers are sending down essentially what time it is, and your handheld receiver is like, oh, okay. It just sent down a signal saying that it is, this exact time, but I know from my internal GPS receiver that it's actually a little bit later than that. And that difference in time is essentially how far away the satellite is based on the speed that those waves are traveling. So that's how this works. And so all your GPS can figure out at first is just how far away a satellite is based on that time delay. What we do is we add in multiple satellites. You lock on to at least 4 of these. And once you have 4 of these, you've got 4 unknowns, or you've got 3 unknowns. You've got your X, Y, and Z unknown, and you know the time. You can solve for X, Y, and Z and plot your position on the surface of the Earth. So again, here you are on the surface of the Earth right here. And with any one satellite, basically you only know where you are relative in essentially a radius around that one satellite. So that's why we lock on the multiple satellites. Get that multiple satellites you lock onto and calculate that timing. And then once you have that, you look at the intersection of where those spheres are, and that is your known position. This is called trilateration. Okay, so GPS signals, or your GPS units, have different amounts of accuracy, and that's because there's different amounts of errors that are introduced to this system of calculating your position relative to these timings. And so we're going to learn that there's ways around this and getting around it. But first of all, let's just talk about where these errors come from before we figure out how we work around those errors. Does that make sense? The first one here are going to be essentially the fact that it takes time for that that signal to come through the atmosphere. But interestingly, it depends on atmospheric conditions. Depending on the time of day and what conditions in the atmosphere, that's actually going to change. So you're going to get some delays in the ionosphere and troposphere. And so we're going to have to correct for that. And we're going to see that some GPS systems have ways of correcting for some of this. Okay, another really important issue is signal multipath. And how this works, let's say this is your GPS receiver right here. Does everyone see the GPS receiver? Okay. So we got the GPS receiver, and then you've got a satellite up here that's sending down the time. But let's say you have not just your GPS receiver, but you've got next to it a tree. So GPS receiver and tree. What if that GPS signal comes down, hits the tree, bounces off the tree, and then reaches your GPS receiver? It's going to be a longer time than if the signal had just come straight down. So that's multipath. And so that can lead to some significant errors if you want to know where you are down to a centimeter in accuracy. And so what we're going to have to do is overcome this multipath problem. And look how simplified that problem is, right? Receiver, pencil tree. That's it. But imagine you've got that receiver and you've got 200 or 300 trees around you, a 400-foot building next to you. You can have lots of multipath errors. So a lot of more advanced, sophisticated GPS systems are trying to account for those multipath signal errors. Okay, we can have clock errors as well, and that's because if you just have your little standard GPS that's in your phone or one that you buy for hiking, it does not have an atomic clock in it like the GPS receiver, the GPS satellites do. And so it might not know the time accurate enough, and you get errors introduced from that less accurate clock. Okay, another really important problem is number of visible satellites, especially when we're trying to get very, very precise positions. You don't want just 4 satellites, you want 10 or 12 satellites. And so you want to be in a part of the world where you can see a lot of satellites spaced out pretty evenly. So that's going to be really key as well. Okay, and finally, we can have what's called satellite geometry, which can create some shading errors. Where here's your GPS receiver here, and then you've got, you know, this satellites way up here. What you want is them evenly dispersed in your skyline, in your sky view. If they're clustered, then that's going to lead to a less accurate determination of your position. So those are some of the other errors. That's kind of the last error I want to talk about today. And so when we start to deploy GPS systems for doing science, doing geomorphology, we have to decide based on a couple of factors what type of system we're going to use. And essentially what we're really concerned about is how precise you need to be and how long and the effort required to collect that data. Because the more precise you are, the more time it's going to take you. And also, I should say, generally cost goes up as well, right? You can buy a GPS handheld receiver for hiking for less than $100. And if you're just going to use, you just need a position, and it's okay if you're accurate with only a couple of meters, 2 or 3, 4 or 5 meters, that's great. If you need centimeter scale accuracy, knowing where you are, you might have to invest in a system that will cost you tens of thousands of dollars. So generally, the recreational GPS, the ones you have in your phone, at best, those are going to be half a meter in accuracy, maybe a little bit better, but generally about half a meter in accuracy. And then survey grade GPS is going to get you down to 10 centimeters to maybe all the way down to about half a millimeter if we're using, or millimeter scale accuracy, I should say, if we're using what's called static campaigns. So we're going to talk about these 3 different methods of collecting data for getting elevation with GPS. Okay, so there's the picture of our handheld, and then our kinematic GPS system, and then a static observation. Okay, so when we're talking about the precision of our GPS, if you've just got your little handheld GPS and nothing else, then your accuracy is only about 15 meters, right? That's about as accurate as you could get just using the GPS satellites themselves. Now, in North America, we have the WAAS GPS system that basically broadcasts some of those corrections for you. And so using that system, that can get us down to about 2 to 3 meters in accuracy if you can see those extra satellites, and those are only basically centered over North America. And this is what your car or your cell phone is able to do. Now, this says 2 to 3 meters. That accuracy really only stands for your X and Y. If you're talking about the elevation, those can be off even more. It's very difficult for your GPS satellites to get that Z value. And so your elevation could still be off tens of meters. There is a way that you can use what's called differential GPS, that you can pick up those corrections for like the ionospheric ionosphere differences, and basically those corrections can be beamed out on a satellite that your GPS picks up, and that can get you down to maybe 1 to 0.1 meters in maybe the best case scenario, but we generally think about that as about half a meter in accuracy. Okay. So if we want to move to that survey grade GPS, that's where things get even more complicated, but that's when we get the real accuracy. And that's what we call RTK, real-time kinematic GPS. And so that's going to be kind of our gold standard most of the time for what we want to do in geomorphology. So how does RTK GPS works? Well, first of all, instead of having just one receiver, you need two receivers. You need two GPS receivers. One is going to act as a base station. It's going to sit in one place, and then you're going to have a rover unit. So here's base and here's rover, okay? So with this, the base station just sits here, and the base station is just getting the timings coming down, right? And so with that, and here it is, here's our base station right here. The base is in a known location, and it's not moving. But every time it gets a signal from the GPS, it might say, oh, no, wait. It says you're 10 centimeters off in the X directions, 5 centimeters off in the Y direction, and 20 centimeters off in the Z direction. But it knows that it's not moving. Does that make sense? And so even though the GPS is telling it maybe it's in slightly different positions on the surface, it's really not. And so it's able to actually make a correction, be like, okay, that's wrong. I know that I'm actually here. What it then does is so there's the base station, it makes the correction, and then it sends a radio wave out with those corrections to your rover, and your rover goes around and it surveys a new point, and it says, okay, this is where I think I am, but then it grabs, based on the GPS, but then it grabs the correction from the base station and corrects that location from the GPS, which gives you accuracy down to centimeters. So here's how that works. We've got our base station right here. We've got our base station that then is going to broadcast out the correction to the rover, and the rover is going to take that known that position it calculates from the satellites. It's going to correct based on the base station corrections, and then it's going to tell you exactly where you are down to a centimeter. So that's kind of our gold standard RTK. It's once you got the network up and running, it's really fast. You can get a point within a second or two, and then move on. We also have what's called network RTK GPS, where instead of a base station you set up, you're going to go find someone that's got a long-term base station set up that is constantly beaming out the corrections that then you can pick up. And so there's a couple of these here in Walla Walla. And so whenever we're surveying in Walla Walla, as long as we've got an internet connection, we can log on and find these base stations that are in real time being broadcast to the internet, and then we can use those to correct our position. So that's network RTK GPS. Okay, so how about applications of GPS using these three different systems? It's going to be different, right, based on recreational systems, kinematic systems, or static systems. We didn't talk too much about static yet. I'm going to introduce that in a second. But really, I'll introduce it right now. A static system is basically you've got a base station, and it just sits there, and it can record its position. You log the position for several hours to a day. And so once you do that, then you can calculate that position down to the millimeter scale in terms of your accuracy. That's if you need very, very, very precise accuracies. But think about that millimeter scale. When do you need to know where something is down to the millimeter? That's really different. Oftentimes in geomorphology, we're pretty happy if we're down to a centimeter, right? A centimeter scale accuracy, or even 10 centimeters, so 2 orders of magnitude larger. So static systems, they're expensive, they're highly complex and long occupations. But if you need that millimeter scale accuracy, that's when you're going to use static. Oftentimes, for what we're doing in class, we'll use basically what's called recreational mapping systems. We'll use those auto levels, but we can use those kinematic systems as well. They're still very expensive, and there's quite a bit of complexity to them. But this is key here: short occupations. You only need to measure for a couple of seconds, and then you can move on. There's our recreational, kinematic, or that long-term where you're basically setting up on a position for several hours to several days. Okay, so let's think about how we can use these in geomorphology. Let's say you've got a landslide. Does everyone see? We've got a landslide right here. So let's say you're in the field with your GPS system. You can use your GPS to essentially hike around and map the perimeter of this landslide. And so what right there, you could maybe even do that with the GPS on your phone and calculate kind of or figure out kind of where you walk to map out the perimeter of that landslide. And then you can take that back to a GIS, a geographic information system, and calculate, do analyses on it, like say, okay, this slide is 64,000 square kilometers in area. So that would be a use in the using kind of the recreational style systems. Let's say you wanted a more accurate system. You could use real-time kinematics, and in this case, we go in and we can measure a bunch of points in there using our RTK GPS and get centimeter scale accuracy. Do lots of surveying, and then actually maybe make a very high resolution, 10 centimeter resolution digital elevation model in a GIS after. So that's what we could do if we had one of these RTK systems. And finally, our last system, our static system. Let's say that you've got a landslide and you want to see if that landslide is moving. You can use it to do what's called change detection, where you set up your antenna right here. There's our antenna sitting up right on a block. And basically you sit there and you measure where that block is, that rock, for a couple of hours, and then you know its position down to a millimeter, and then you can come back a year later, make the same set of measurements again, and see if that block has moved. And so that might be something we could use to tell us if there's a slow-moving landslide and maybe it's speeding up and something we should be concerned about. So this would be used for essentially change detection at the millimeter scale. Okay, so that's all I'm going to say about GPS. Take a deep breath. I want to talk about a couple of different ways we can generate elevation data and survey data using what's called active remote sensing. And so active remote sensing is when we're actually going to be sending out some sort of signal from either a plane or a car or a satellite, and then collecting from that. So our first active remote sensing system I want to mention is SAR, synthetic aperture radar. And so this is generally mounted to an airplane or a satellite, or in this case, the shuttle. And how SAR works is it basically beams down radio waves that then we collect the timing and how long it takes for those waves to be reflected, and we can calculate elevation very accurately using SAR systems, really down to with modern systems down to tens of centimeters. And so I mention this because these SAR systems are really important. The Shuttle Radar Topography Mission, SRTM, was really one of these first SAR systems deployed in space, which gave us our first ever global digital elevation model, knowing elevations across the globe from the same system with a very, very high degree of accuracy. So I just wanted to mention these SAR systems. But another one that's really important that you've probably already heard a little bit about is LiDAR. So in radar, you get radio waves that you're bouncing off a surface, and LiDAR, you have light, and so lasers are what are bouncing off a surface. So, oh, we lost our video. I'm going to pause this, and then we'll come right back for part 2. For 4, for 5 laser pulses, it sends out tens of thousands of LiDAR pulses each second, and then can measure the return of those light pulses. And so this is our new gold standard for collecting elevation data at a high level of accuracy, because essentially you can send a plane up over a hill slope and get a laser pulse at every square meter, and basically be able to tell that where you are in that square meter with accuracies down to a centimeter to tens of centimeters. It's really, really awesome, these LiDAR systems. And so they've revolutionized our ability to get high accuracy elevation data relatively quickly, right? Because you can do this more than once, right? You can fly the plane again, so you can do change detection using LiDAR. You don't have to just mount these to a plane. You can mount them to a car as well. And this has become part of the autonomous car wars. Whether you need LiDAR on cars, Google, well, I should say Alphabet, they use LiDAR on their cars. This is a Google car here. Musk and his company Tesla, they don't use LiDAR in their systems, and Musk has kind of said that they don't need them. So that's kind of where you might have heard about these in the news right now. But these are really cool because you can use them to essentially in real time scan a city block. And so this can be used in construction applications and mining applications. I have a friend who started a LiDAR company in New Mexico, and they wanted to do science, but there wasn't that much money in it. So actually where they were making their money was they were getting hooked up with movies that were in production, and they were scanning the real-time movie sets where they were shooting a film, and basically building that first 3D model of the set that then would go in and use as the base for all the CGI crap they smear on top in the movie. So LiDAR is not just used in geology, it's used everywhere now, and it's a really cool technology. You can also have ground-based LiDAR systems as well, and those are really useful for measuring kind of a hill slope. If you got a hill slope that's moving, you could set up your LiDAR and collect repeat data to characterize if you've got a landslide, slow-moving landslide happening. Okay, the other cool thing about LiDAR is you're going to get returns on whatever it bounces off. So if here is the surface of the Earth right here, and then here's our tree again right here. You got your LiDAR pulse coming down. One's going to hit the tree and come back. One's going to come all the way to the ground and hit the ground and back. And you're going to get that data from the vegetation as well. So with LiDAR, we have the potential for mapping out, say, forest canopies and understanding kind of the structure of a forest canopy at a millimeter scale resolution. So it's going to be able to revolutionize our way of kind of mapping the world around us. So LiDAR is very exciting. Okay, the last one I want to mention is a sort of passive remote sensing, where instead of sending out a laser pulse, we're just collecting light that's reflected off the surface, taking a picture. But that can actually be incredibly useful. And this has been revolutionized by our ability to use UAVs now. So unmanned aerial vehicles, drones, allow us to send up our own little vehicles that have cameras on them, and then we can collect pictures of a site. And so this is a picture here. And the cool thing is that this is from a construction site. You don't just take one picture, you have your drone fly in a line and collect a grid of pictures at regular spacing so that you know you have about 80 to 90% overlap. And the cool thing about that is not only can you make a high accuracy like map or air photo of this, of whatever you're taking pictures of, but because of that high amount of overlap, you're going to have the same point in a bunch of pictures. And so you can feed all those images into a computer program. And we have this capability in our lab here at Whitman. And basically it can identify the same rock in, say, 10 pictures, and it knows if it's where one rock is, and it'll find another rock, and it will see how the difference on the image changes between those 2 points depending on where the camera is moving over top of you. This is called photogrammetry. And so once the computer program knows where the camera is for each picture, and knows those relative differences in where points are in the pictures, it can actually extract the 3D position. And so you can make 3D models from two-dimensional imagery. And we'll talk a lot more about this during the semester because it's a really, really cool technique. And really, it's only been in the past 10 years because of drones. We've been able to do this relatively cheaply. Remember, I talked about the cost of some of these GPS systems or a LiDAR system. A LiDAR plane is going to cost you hundreds of thousands of dollars. Here, you can get a drone that can take these pictures for a couple of $100s these days. So it's really kind of opened up our ability to do this type of work. So as I mentioned, we do this in our lab here. And so we kind of combine our drones with our GPS systems. And that's really cool because what we do is we set out these mats. So here's these mats, and we'll use the GPS here to survey where the mat is. So there's Christoph with a mat. And then when the plane flies overhead, it's going to see those mats, and then we can mark where those are in the imagery, and we have the known position. So we can make highly detailed 3D models of the landscape that have a centimeter to a couple of centimeters resolution. So it's really kind of changed our ability to very quickly, relatively cheaply get high accuracy 3D models and 3D data that then we can use to understand geologic processes at the surface of the Earth. So we'll be talking a lot more about this semester. All right, well, I hope you enjoyed our first exploration into the tools of geomorphology. Have a great time, and we'll talk to you soon. Bye.